Okay. Now, the little thing in the margin that nobody ever looks at. Integrating rational functions. I'm on page 332. Early in chapter 4, you learned rules that allowed you to integrate any polynomial function. The log rule presented in this section goes a long way toward enabling you to integrate rational functions. For instance, each of the following functions can now be integrated. And then look, they tell you what the function is, and they tell you which example in the book shows you how to integrate each one of these. This is one of those sections where you're going to have to read the examples in the book, because this can be used in so many different ways. I cannot work an example of every type of way where there's just not enough hours in the day. Okay? So you're going to need the examples I work, and you're going to need the examples in the book. When you read the examples in the book, you've got to think as you read. All right? You've got to read the directions. You've got to read each step. You got to think, okay, why did they do that? Or how come they're allowed to do that? You've got to figure it out as you go. Otherwise, just looking at it, which is what some people do when they read something that's kind of difficult, you just kind of say the words in your head and you don't stop to think about it. Well, don't bother, because it's not going to help. Okay? So you're going to need to read these examples carefully, slowly. It'll take you a while. I do want to go over some of them with you. Example 5. I know how much you guys love long division with polynomials. So when you look at example 5, if you try the things we've done in the past with a u, you'd say let u equal x squared plus 1. So then du would be 2x dx. I don't want the 2. I can get rid of that. But, you know, that can't all be replaced by x dx, can it? So they do some long division. They rewrite the whole thing. Then they're back in business. So don't try long division as your first option. But don't forget it's an option. Okay? All right. This is, see, where did I copy this from? Page 335. As you study the methods, shown in examples 5 and 6, but all of them really, be aware that both methods involve rewriting a disguised integrand so that it fits one or more of the basic integration formulas. So we're still having to rewrite things. Doing our change of variable substitution didn't solve everything. That's still going to be the technique we use almost every time, but quite often we're going to have to rewrite it before we can figure out what u equals. Throughout the remaining sections of Chapter 5 and in Chapter 8, much time will be devoted to integration techniques. To master these techniques, you must recognize the form-fitting nature of integration. You've got to memorize the formulas, because if you don't, you won't recognize what you're able to integrate and what you're not able to integrate. Okay? I mean, it's kind of basic. When we did geometry, you had to recognize a triangle. So, okay, I can do all the stuff with triangles on this. You had to recognize a parallelogram. Okay, I can do all the parallelogram stuff with this. Well, you've got to recognize, hey, that's a 1 over u. I can do the natural log thing. Okay? In this sense, integration is not nearly as straightforward as differentiation. Differentiation takes the form, here's the question, what is the answer? Integration is more like, here's the answer, what is the question? So we are now playing Jeopardy. Or backwards. All right, then these following guidelines. Learn a basic list of integration formulas. All right, so you're going to have to know the integration formulas. Remember that cheat sheet I gave you with all the trig stuff on it? The flip side of it is derivative and integral formulas. You need to know those. And then you look for a formula that resembles all or part of the integrand. And by trial and error, you figure out what u equals. Yeah, lots of frowny faces. Takes effort. Right? Are you going to choose the correct u first every time? No, neither do I. Well, I do now because I've got them all worked out in my notebook. But the first time I work a problem, sometimes I do not choose the correct u, and I've been doing this a really long time. Okay? If you cannot find a u substitution that works, that's when you try rewriting the integrand. All right, and there's all different ways you can do it. If it's trig functions involved, try trig identity. Try multiplication, try division. This is a cool one. Addition and subtraction of the same quantity. Okay, wonder what that means. And then number 4 means cheat if all else fails. If you have access to computer software that will find antiderivative symbolically, use it. No. That's not allowed in any course you're ever going to take in college. It's not allowed in the AP test. So they might as well have just said copy from somebody that's smarter than you, because that's not allowed either. So I don't know about number 4. Now, did you ever wonder why we didn't know what the antiderivative of tangent or secant or cotangent or cosecant was? You know, when you get together on a weekend hanging out, you probably discuss those kinds of things. I wonder why we don't know what the antiderivative of tangent is. And then you all sit around for a while and you wonder about it and you come up with your own theories. And, well, here's why. We hadn't talked about natural logarithms yet, so it would have been silly to talk about these integrals considering that they result in natural logarithms. And not just natural logarithms of trig functions. I mean, come on, how cool is that? All right? I mean, that is nerd cool if there is if there is such a thing as nerd cool. So, there you go. And even better, in the old days, the formulas look different. Like, those are not the same. Now, even before my day, I think these were the same formulas I learned. How can they have 2 different formulas for the same trig function? Okay, but how did they magically move the negative sign? They use computer software. They use logarithm rules. All right, the negative in front is the same thing as an exponent of -1 at the end. And then once you get an exponent of -1, you can then do things with that, which I don't want to go into, because it takes a while to prove that those are equivalent, but they are. So if you happen to be rummaging around and when you go to college next year, and, you know, just for kicks, you're going through the school's library and you find a calculus book from like 1890, they might have that one as the formula. They might not have invented integrals back then, though. I'm not sure. When did Newton live? 1700s? 1600s? BC? I don't know. It was a while. Let's do some examples. Page 338. We'll begin with number 11. The directions are really complicated here. Find the indefinite integral. All right. We have the integral of x squared plus 2x plus 3, all that over x cubed plus 3x squared plus 9x dx. All right, first thing I'm going to try is a straightforward substitution. I'm going to let u equal something. Now, we tend to let u equal a quantity with an exponent. I suppose the quantity in the top has an exponent of 1. What's the quantity in the bottom have an exponent of? -1. Seems a little more interesting, doesn't it? More likely to be u. A quantity in the denominator is more likely to be the u than a quantity in the numerator. More likely. Does it work that way every time? No. Okay. And I mean if there are no other exponents showing. Okay? So let's see here. If I let u equal x cubed plus 3x squared plus 9x. What does du equal? Yep. Put it in a parentheses and put a dx behind it. On the last quiz, some of you got yourself in trouble on a couple of difficult integrals by never addressing the du issue. So you were off the rest of the way. So you've got to write that down and write the notation properly. You guys are getting better at writing the proper notation. Room for improvement for most of us. Okay? All right. Is that what we hoped it would equal? What do we have to do? Factor out of 3. So du equals 3 times the quantity, x squared plus 2x plus 3 dx. All right, at this point, the only thing between us and what we hoped du would equal is that constant of 3. So multiply both sides by 1/3. All right, now, you just keep writing straight down your page. I'm going to write out to the side here so you can try to watch me think my way through this. So I'm going to do the substitution, have the integral up. All right, first thing I'm going to do is I'm going to take that denominator and I'm going to replace it with u. And now I'm going to take x squared plus 3 dx, x squared plus 2x plus 3 dx, and replace it with, no, not du. Not 1 du. 1/3. Now, watch this though. 1/3 times 1 is 1/3, isn't it? Can't just leave a blank numerator. Okay? So a factor of 1 works nicely because 1/3 times 1 is the 1/3 that we needed. du. You with me on the substitution? All right. So we leave the 1/3 out in front. What is the integral of 1 over u du? Natural log, absolute value of u, plus c. Remember? Remember? So that gets us this far. And what's the only thing left to do? Put the x's back in for u. And there we go. Hannah, question?
Yeah, could you also write that as like the whole quantity cubed?
Not cubed.
Not cubed to the 1/2.
Yeah, you could change that to the natural log of the absolute value of x cubed plus 3x squared plus 9 to the 1/3 plus c. Yep. Which is a good point because you may look at this up in the back of the book, and I don't know which answer the back of the book has. Okay? So, you may have the same version or a different version of the same answer. And does it? Okay? Now, if I was certain that the quantity inside the absolute value sign was positive, would I need the absolute value sign? No. Am I certain that x cubed plus 3x squared plus 9x is positive? No. What if x is like negative 1,000? Negative. Okay? So leave the absolute value signs. When there's any doubt whatsoever, leave the absolute value signs. Okay? Only if you're absolutely certain that the quantity is positive should you eliminate the absolute value signs. Let's do another one. Yes? Why isn't it NL? I blame France. All right. On this one, I'm going to use division to rewrite this. If I let u equal x plus 1, then du would be dx, and I'd still have to mess with that x squared minus 3x plus 2, wouldn't I? So I'm going to try long division. I'm going to divide like so. So I'm going to divide x plus 1 into x squared minus 3x plus 2. All right, here's how it works. X squared divided by x, that's what you're looking at. First term, first term. X squared divided by x is x. Then you turn around and multiply. X times 1 is x. X times x is x squared. Then you bring down the 2, and then you subtract. Negative 3x minus x is negative 4x. And then I do the division again. First term divided by first term. What's negative 4x divided by x? Negative 4. And you multiply. Negative 4 times 1 is negative 4. Negative 4 times x is negative 4x. All right, subtract. 2 minus negative 4 is 6. Negative 4x minus negative 4x is 0. So we have a remainder of 6. What does this tell us? It tells us that our expression can be rewritten as the quotient plus the remainder of 6 over the divisor of x plus 1. So it's what's on top plus the remainder over the divisor. All right. I can find the integral of x. I can find the integral of 4. Can I find the integral of 6 over x plus 1? I think so, if I let u equal x plus 1. All right? So, the integral of x is 1/2 x squared. The integral of negative 4 is negative 4x. Now, as you're about to see here, I didn't write down my substitution for this next step. Because here's what I was thinking in my head. I said, all right, if I let u equal x plus 1, then du equals 1 dx. Okay? So that 6 on the top, just leave that as the 6 in front. I can integrate that. All right, I've already planned it out in my head. That's 1 over u du, isn't it? Okay? Now, I'm in dangerous territory here because it's one of those things where do I need to write that down or don't I? You probably do. Okay? So when I looked at this and saw that I'd not written that down, I kind of cringed because you probably need to write that down. All right. So I've got the 1/2 x squared minus 4x plus 6. All right, if I've got the integral of 1 over u du, even if I have it written, so what I should have done is, okay, so that's 6 out in front, 1 over u du, keep the 6 out in front. That'd be the natural log of the absolute value of u plus c. And what was u? X plus 1, so that's 6 times the absolute value, or the natural log of the absolute value of x plus 1 plus c. All right. Not so bad. Now, you don't have to write this next one down, the or part. I made the substitution work. All right. So if you're terrified of long division, this particular problem, you can work around the long division. Now, let's do a side-by-side comparison here. You know, it works. I let u equal x plus 1, so then du is dx, but then I would be stuck with all that I can't replace, right? If I try the substitution at that point, I've got the integral of u, dx is replaced by du, and then I've still got x squared minus 3x plus 2. So x equals u minus 1. All I did was subtract 1 from both sides right here. Then replace all those x's with u minus 1s. Multiply that all out. Combine like terms. End up having to do division anyway. U squared divided by u is u. Negative 5u divided by u is negative 5. 6 over u. Hey, isn't that what I had there? So this way's a lot longer. I'm not sure it's more difficult. That's tricky. You got to remember to do that. But just because it's longer doesn't necessarily mean it's more difficult if you can't do the long division. Does that mean that you can always avoid the long division? No, it does not. Okay? You could in this case. Number 24. All right, I really don't want to have to do long division this time. Okay? In fact, I can't because I'll have an x cubed on the bottom if I multiply all that out. All right, so I'm going to have to find a u that works. See two quantities. I see one of the quantities in the denominator and with an exponent. So which quantity am I going to try first? The one in the denominator with an exponent. So let u equal x minus 1. If we let u equal x minus 1, what's du equal? That's dx. Is that good enough? No, because if we try the substitution now, I can get u cubed in the bottom. Got that. I can replace the dx with du. But then I'm stuck with the x's. I'm stuck with an x times an x minus 2. I can't do that with two different variables in there. So what do I need to do instead? Solve for x. So if u equals x minus 1, what does x equal? U plus 1. So instead of those x's I was stuck with a minute ago, replace them with, so replace that x with u plus 1, replace that x with, oops, not x plus 1, idiot, u plus 1, don't forget the minus 2, like so. All right. Well, back in my day, u plus 1 minus 2 was u minus 1. What do you think you ought to do next? Yeah. Multiply it out. Squared minus cubed. D, divide. All right, and here's how I want to write it. All right, you keep going down your paper. I've got the integral. What's u squared over u cubed? Yeah, it's 1 over u. It's u to the negative 1, but better yet, it's 1 over u. We know how to integrate 1 over u now. And then what's over u cubed? Either call it 1 over u cubed or call it that, because we know how to integrate that, right? But we also know how to integrate 1 over u cubed, because in your head you know it's u to the negative 3 du. Oops, see, I didn't even rewrite it that way when I did it. Then I did. Okay? So, what is the integral of 1 over u? Natural log of the absolute value of u plus c at the end. Don't forget to take the integral of negative u to the negative 3, add 1 to the exponent, makes the exponent negative 2, divide of negative 1 by negative. Don't forget the plus c. Also, don't mess up the should already know how to do. We're supposed to already know how to do that. So try not to blow it there on the quote-unquote easy part. Are we done? Now replace u with x minus 1. Also get rid of that negative exponent if you don't mind, please. Even if you do mind, actually. Oh, so this is kind of fun, right? So you can go ahead and make your weekend plans now. Get together, do some integration. Number 27. Now, I'll warn you about this. Don't do your calculus homework at the Murray State game. Because if you do, especially you guys, you're going to be hit on by college girls. Because they'll think, ooh, look at that. Blake is so smart. He does calculus. So, I mean, bring some mace or something to keep them off of you. All right. What do you think? What are you going to let u equal, if anything? They're written a quantity with an exponent on it. X is not a quantity. It's an x. Don't let u equal x. That accomplishes nothing. There is a quantity in the denominator. And we know how to take the integral of 1 over u. Or so maybe it's as simple as that. Maybe u is just the square root of x minus 3. So let's try that. Well, then what's du equal? Now, we're to the point now where you're going to have to memorize what the derivative of the square root of x is. All right, so if u equals square root of x minus 3, what's du? That square root of x is the same thing as an x to the 1/2. So we would power rule it. We'd make that 1/2 x to the negative 1/2, derivative of negative 3 is 0, dx. But we can simplify that a little bit. So wouldn't du be 1 over 2 square root of x? So you need to memorize that. It's going to come up often enough that you're going to be frustrated if you have to figure it out every single time you run across it. The derivative of the square root of x is 1 over 2 square root of x. Okay? So that's our du, 1 over 2 square root of x dx from. All right, I like the fact that I have a dx in there. I'm not loving the 1 over 2 square root of x. The square root of x, okay, but it's in the wrong place. Shouldn't it be in the numerator? I can multiply both sides by 2. I can also multiply both sides by square root of x, which leads to its own set of problems. Let's pretend that we were going to stop right now and do our substitution. All right? The denominator, square root of x minus 3, we're calling u. The dx can be replaced with 2 out there, du square root of x. Don't like that square root of x. But wait, what can I replace the square root of x with? Not minus 3. Yeah, go back to right there, add 3 to both sides. And does that give you that u plus 3 equals a square root of x? Don't even solve it for x. Isn't it the square root of x that I'm trying to replace? So, replace that square root of x with u plus 3. And now I can make the substitution. So, let's make sure that we follow me. So here we are. Let's pretend I hadn't done that, because maybe you guys probably don't write stuff out to the side just to see if it works, do you? You probably should, but nobody does, except me. All right, so let's see here. If I make the substitution now, the square root of x minus 3, I can replace with u. Okay? The dx, let's see, let's make sure I get this right. The dx can be replaced with 2 u plus 3 du. Okay? Oh yeah, I was supposed to replace that with something. Sorry, I messed it up a while ago, didn't I? I forgot about that extra. Sorry. All right. Did y'all see Will Ferrell introducing the somebody's last night? He was making, well, I guess it was written out, but he was like, and number 5, he still lives with his mother, and then the player's name. It was hilarious. You know, that guy was like, oh man, I'm never going to get a date now. I'm 33 years old, and I think I live with my mother. Ah. All right, so now I got to replace that other square root of x with another u plus 3. Well, this looks interesting. I wonder if I'm going to work this and then for a while and then stop and then have an or written and do it a different way that actually works. Could it be? Let's try this one. Let's not give up yet. All right, what can I do with that 2 that over here I stuck in front like I should have? Stick that in front. U plus 3 times u plus 3 is u squared plus 6u plus 9. Denominator is still u. Now what do I want to try? Starts with a D. Division. Yeah, let's not differentiate. Kind of defeats the purpose. All right, u squared. Die. No. Destroy. U squared divided by u is u. 6u divided by u is 6. And 9 divided by u is either 9 divided by u, or if you want to get a head start on how you're actually going to integrate that, 9 times 1 over u. 9 over u is fine. Still got the du at the end. Can we integrate this? Yes, we can. Because keep the 2 out in front, then the integral of u, power rule that one, 1/2 u squared. The integral of 6, that's a form of the power rule, 6u. The integral of 9 times 1 over u will be 9 times whatever the integral of 1 over u is. And we know that now. The integral of 1 over u is the natural log of the absolute value of u plus c. All right. Now, should I keep that 2 factored out in front, or should I distribute that 2 back into the parentheses? I am going to distribute it. Why? Because normally I wouldn't. The only reason I'm going to is because it gets rid of a fraction. And anytime I can destroy a fraction, it's a good thing. So I'm going to do 2 things here. I'm going to distribute the 2 back through to get rid of the 1/2, and I'm going to do what with the u's? Replace them with the square root of x minus 3 to get that. And next I'm going to actually I rewrote it so I could read it better. All right, let's wrap it up right there.